Okay, so last time we went through what I call the messy mathematics of spectroscopy. We went from the experimental spectrum, which was the black body radiation curve, all the way down to the wave function to kind of show that the wave function was involved in the energies, which was the differences in those energies was the x-axis where each transition took place. Those transitions are called lines, spectral lines, which goes back to Bunsen's experiment. And then the y-axis is what's not typically covered in textbooks. It's the transition moment integrals, whether it's a dipole moment in direct absorption or emission, or scattering moment or polarizability operator in scattering. It's still, I call it the transition moment calculation. That's the y-axis. And it's the overlap of the upper wave function and the lower wave function. And so wave functions are involved in the y-axis too. So we really couldn't explain anything about spectroscopy without the wave functions. We didn't talk really about the wave function and where it came from or what it means. And so in Schrodinger's paper, he laid out these postulates of quantum mechanics, and that's what we're going to be talking about today. But it sounds really dry and boring that we're learning the foundational assumptions of quantum mechanics, but I think it explains two things. If you're confused by quantum mechanics and looking for explanations, a lot of these things are just taken as a given. They're not really explained. Okay? So that's why you sort of reach this point about what is the wave function? What is the probability distribution? And why is the square of the wave function the probability distribution? It's what we assumed to start. And so that's what we're talking about today, is the foundational assumptions of quantum mechanics. And so that's what we mean by postulates. Is that a postulate, like you could use it as a verb to postulate something. That's to suggest or assume the existence, fact or truth of something, or it could be a noun. So these things that are assumed to be true as a basis for reasoning or discussion. So that's what we're talking about today. These are the foundational assumptions for quantum mechanics. In mathematics, a similar thing. It's an assumption used as the basis for mathematical reasoning. So these were lined out in Schrodinger's paper, and from that point forward, these were the baseline assumptions. We haven't proven that the wave function exists, but it is so useful in explaining our observed phenomena. So we can't really get into a particle and see if it's behaving like a wave without using spectroscopy. So it explains the tool that we use, but there's no way to get even any deeper than that, really. And this lecture covers the postulates that are the basis for quantum mechanics, the math of wave mechanics. So there's 4 or 5 postulates. We'll go through them one at a time. But the postulate is easily stated, and then there'll be lots of things that fall out of that. So today is the day when your calculus prerequisite comes into play. And so we'll do a little bit of calculus today. We'll take some derivatives, we'll do some integrals, and I'll walk you through. I try to not skip any steps, because that's frustrating. Whenever you're reading math in a book or in a paper, they show kind of what I did last time. I showed the messy mathematics, but I didn't solve any of those equations. I just showed them to you. Well, today we're going to solve some of the equations. So this is postulate number 1. The state of a quantum mechanical system is completely specified by the wave function. It doesn't explain why. It's just an assumption. That's our ground level postulate. That a quantum mechanics system can be explained by the wave function. So in any case, whether it's vibrational motion or translational motion or rotational motion, each one of those phenomena will have its own wave function. So everything an atom, ion, or molecule does, or an electron, has a wave function. Even the nucleus has a wave function. That's how we describe quantum level objects. And then the square of that wave function, and it's the square modulus, because some of these wave functions are complex. And so this little star here, in Excel, this little star means multiply, but in quantum mechanics, this means complex conjugate. And you can learn more about that if you read that chapter that I've assigned in reading. It talks about the complex conjugate and how you just change the sign of I everywhere it occurs in the wave function. Okay, so the square modulus of the wave function, we could just say the square of the wave function, is the probability distribution of the particle described by that wave function. So think of the two words, probability and distribution. What is distribution? It's how you distribute things. So if we have particles in a system, it's the distribution of those particles. And the probability piece is, we don't know where an individual particle is, but on average, we can take samples after samples and we can get an idea of where that particle is. So it's the probability distribution or the probability of finding a particle in a particular area in that quantum system. Now, if we integrate over the whole area of that system, the probability should be 1. And that's what we mean by a normalized wave function. We square that and we integrate over the whole space. And for a single particle, we better get the number 1, right? We've integrated the probability of finding that particle anywhere in the box, and we have 1 particle, so we should find that the square of the wave function integrated over all space should equal 1, or 100% probability of finding that 1 particle. Now, if we have time involved, then it's also, there's a time function. So the probability that a particle will be found at a given time in a spatial interval is given by the square of the wave function with time involved. You see there's a t added in there. So the probability of finding a particle over all space is 1. And so this is our worst case scenario of our wave function, that it would be a wave function that's in 3 dimensions, so x, y, and z, and time. So it's moving over time. And so it would be a quadruple integral. And this would be one ugly looking thing. It's easy to write psi of x, y, and z, and t, but its dependence upon x might be some exponential function, and on y might be some cosine function and sine function. So it can be all of these functions multiplied by each other in a really difficult integral. So that's what Dirac was saying. These equations are much too hard to solve. And so we need to find simpler methods for explaining the math. So that's why we focus on the particle in a box. And we just reduce it to 1 dimension. And we can do easily an integral with 1 dimension. Okay. That's the calculus that y'all had. Cal 1 and 2 were essentially over 1 dimension. When you get to Cal 3, then you have multivariable calculus, where you have to do double and triple integrals. So let's talk about this wave function a little bit. So these are invalid wave functions. Just think about it. Is that going to produce a wave? Like an oscillating wave, if it's broken in the middle? Think of a jump rope. That would be a crummy jump rope. Okay? Or if your jump rope was kind of like a wire and it had a kink in it. Okay, we can't have any kinks in our wave functions. Now, what that way you describe a kink is that the first derivative is not continuous. So if I'm taking the slope of this curve right here, so the instantaneous slope goes like that, right? And I get to this point and the slope is going down. That's if I approach it from the left. So the slope is negative, right? What if I approach it from the right? The slope is positive. At this point, the slope has 2 values. It has a negative and a positive number. So if we're going to take the second derivative of this wave function, which we have to do in the energy, the Schrodinger equation, that second derivative is not going to be defined because it's going to have 2 values. So we can't have any kinks in our wave function. Do y'all understand what single valued is? If I pick an x right here, my wave function has 3 values at that x. So we can't have a loop in our jump rope. And then it can't be infinite anywhere in between the boundary conditions. So this wave function is not finite. So those are the 4 rules that will break a wave function. So if your function doesn't break any of these rules, then it's a valid trial for a wave function. You could put it in there and you could see if it matches the energy. And if you try a different wave function and it gets closer to the energy, then that's a better wave function. So wave functions for electrons, nuclei, atoms, molecules have been developed, and they must be continuous, must have a continuous first derivative, must be single valued, and be finite. So let's build a wave function from scratch. Let's just pick a function that's easy to know, like a sine function. So here we have a sine function, and then we have a box at 7 angstroms long. I just picked a number 7. Okay. So if we plot that, what does it do? Well, it goes up just like a sine function, and it crosses 0 at, do you know this number? It's a little bit larger than 3. Where does it cross 0? Pi, exactly. So 3.14, so that's pi. And where does it cross it again? At 2 pi. Okay, good. And 7 is neither pi or 2 pi, so it's not 0 at the endpoint. So that's a problem. It is finite between 0 and L, so we match that requirement. It is continuous. It has a continuous first derivative, but this is sort of a new requirement. So it matches our requirements for the wave function, but it doesn't match the boundary conditions. So it needs to be 0 at the boundaries. Okay, so let's figure out how we can do that. If I divide that x by L, then it'll go through 0 at pi. So we take that x, we multiply it by pi right here. And so when x is equal to L, then that's equal to 1, and 1 times pi is pi, so we have the sign of pi. So when it gets to L, the length of our box, no matter what our box length is, when x equals the box length, it comes down and hits 0 at pi. Okay, so that's a way to sort of make it fit within the boundary conditions perfectly, is we just divide x by L. Okay, but it's not centered on 0. And later on, when we get to symmetry, I'd like for our wave functions to be centered on 0, so you could determine if they're what we call even or odd. And you'll see some discussion of that in the book, and we'll do that in a future lecture. But let's figure out how we can move it to the center. So I actually want 0 to be evaluated here in the middle. And so what is here in the middle? That is another half pi unit, right? If this is pi, then this is pi over 2. So let's add pi over 2 to our argument in there. So when we add pi over 2 inside the parentheses, that shifts the wavelength to the left by half. And so now when I plot it from minus 3.5 to positive 3.5, that's a width of 7 angstroms, it's centered on 0. So that's a way to shift the wave function to get it centered on 0. So we have our wave function. It's 0 at the left side of the box, 0 at the right side of the box, but it doesn't have any quantum numbers. So it's not going to do anything. We can't increase the excitation of this wave function. We can't decrease it. So we need to add in a quantum number. So if I wanted to go up and down, like up and then down, I need it to not go to pi, I need it to go to 2 pi. What if I wanted to go up, down, and up? Then it needs to go to 3 pi. What if I wanted to go up, down, up, down? It needs to go to 4 pi. So I can just put a quantum number in front of that pi, and it'll bounce that many times. So we can add that quantum number, and we need to also add that to the little phase shift. And here we have quantum states of 1, 2, 3, all the way up. N can go all the way up. It starts at 1, but it goes all the way up to infinity. So we've built a wave function for a particle in a box. So that's what we have here. It's finite between 0 and L. It's continuous. It has a continuous first derivative. It's 0 at the boundaries. It's centered on 0. It has quantum numbers, but it's not normalized. Now, if I were to square this wave function, the negative parts become positive. And if I integrate all over the whole box, I need to get 1. But if you look at this wave function, the maximum values of all of those wave functions is already 1. So I can't get the sum of the area under the curve equal to 1 if the maximum of the curve is already 1. It's going to be greater than 1. So we'll normalize this in a second. But for now, I just kind of want to show what happens to this wave function over time. Can I get you to join me here? So once you stand right here on the edge of this, and hold it. So this is going to be our, hold it high because I'm going to get it on the video. Okay, so this is our ground state wave function. And I'm looking at it really in the real plane. So the real plane is going up and down. When we add time in, we get an imaginary component. So the imaginary plane is forward and backwards. So scoot forward just a little bit right there. So I'm going to add in the imaginary component. You see how it's rotating? So it's the real part's going from maximum to minimum through 0. But your mind might be thinking, well, what happens when it's at 0? Well, that's just the real part's 0. It's actually in the imaginary plane at 1. And then when it's in the real part at -1, then the imaginary piece is at 0. And then when it's in 0 again, it's in the imaginary negative I. And so it's going in the imaginary plane with time in kind of a circular motion. Okay, so don't be confused. It's like, well, if the wave function goes up and then down, what happens when it's right in the middle? That's when it's in the imaginary plane. Now let's see if we can get the second quantum state. So I'm going to just, you stay like a rock wall, okay? Don't move, okay? So that's the ground state, and I'm going to excite it. Ready? See, I had to go faster. There it goes. So that's state 2, n equals 2. So y'all can see that up on the screen, right? N equals 2. Let's see if I can do 3. There it is. Can you see it? Is that 3 or 4? I can't tell because I'm 3. Should I try 4? See how much faster I got to go? Hold your hand high. Got to find the right frequency. What's that one? 4. Yay, good. I don't want to go any higher. Right up in the back in the face or something. So those are our wave functions, and that's what's happening. I say that's what's happening. We don't know if that's really happening in nature. But the math matches the experiment. And the experiment's the only way we can tease out the behavior of these quantum objects. So it appears that they act like waves, but they're unlike waves in other senses because every wave we experience in nature decays, right? You drop a pebble in the water and there's a frictional force and it dies out. You make a loud sound and over distance it dies out. You send a radio wave, your radio stations don't go forever. They die out, but that's because they're interacting with particles and scattering and becoming disordered. We send light into space, it does seem to go forever. So, but these wave functions, there's nothing making them go. Like for that Splinky, I had to really make it go. So this, if you take it too far, leads to philosophical and religious assumptions. Like, what is the wave function and what makes it go? We don't know, because it's just a foundational assumption. Some physicists say it's just a mathematical formalism. They say, shut up and calculate. Don't worry about the metaphysical understanding of what a wave function is and what it's doing in nature. And others, maybe they're Platonic realists, or maybe they're religious, and they say, well, this is the violin strings of the universe that a deity is playing. And so you don't know. That's not in the math. In the math, we start with that assumption, but philosophically, what the wave function means, we don't know. Okay. But the doors are open for all of those interpretations. Okay, let's take a pause here and pass this sheet out. I want to get everybody's name. So just sign your print very clearly your name and then pass it behind you. Do it in order, because I like to learn the names, and this is the best way I can do it.
First and last of this verse.
First and last, if you would, so I can compare it to the roster. Now, everybody in this group here, the first 2 rows. Break my neck. Okay, ready? 1. Everybody look this way. 1, 2, 3. Okay, good. Got the first 2. Don't tell my wife. She'll be really upset. It's a little bit of a high start. I don't need to slow for this. 1, 2, 3. Okay, good. Now compare the picture to what you wrote, and then I can burn your names. Okay, let's get those sheets. Thank you. All right, back to work. Okay, so now we get to do some calculus. So you know, we said that this wave function needed to be normalized. So if we square it, which is what's shown at, you know, psi times psi, squared, integrated over all space, which in one dimension is just x, we should set that equal to 1, and we can solve for this constant in front of the wave function called the normalization constant. It forces it to go to satisfy this condition. So another way to write that, remember Dirac notation, the angle brackets? So that's a simplified way of writing the first line. It's just using the angle brackets. That means integral over all space. And then we just show the quantum numbers, n prime and n, and it's equal to 1 when n prime equals n. And orthogonal, we want each individual wave function to be independent of each other. So wave function 1 can't be like the sum of wave function 2 and 3. So this is a way to say that. It's orthogonal. N prime and n, when they're not the same, is equal to 0. So the wave function we've built satisfies that, but we can prove it in a minute. Okay, so in one statement, this n prime n, integral over all space, is equal to this delta n prime n. So this is called the Schrodinger delta, and it's got this definition. It's essentially those top two lines. The Schrodinger delta is equal to 1 when n prime equals n, and 0 when n prime is not equal to n. And so this is the simplified version right here, mathematically, in one statement of orthonormality. So you have orthogonal here and normal all in the same word. So this is the orthonormality condition, is this little statement right here. And that's a pretty condensed shorthand, but I'm just trying to explain that. Now let's look at this visually in Excel. So if we do these integrals in Excel, which you'll do, I think it's lab 3, you'll do this in Excel and you'll see this matrix come out that we're going to see here. This right here is showing that when wave function 1, so let's just pick up here, when wave function 1 is multiplied by wave function 1, n prime equals n, and the integral over all space is 1. But when wave function 1 is multiplied by wave function 2 and integrated over all space, the integral is 0. And when wave function 1 is multiplied by 3 and integrated, it's 0. 1 times 4 is equal to 0 when it's integrated over all space. So this whole matrix here is captured in that one statement. The integral over all space, when n equals n prime, is 1, so that's the diagonals. Anything off the diagonal is 0. Let's normalize our wave function. So this is our calculus, our first calculus problem. Exciting. So there's our Dirac notation, integral over all space equals 1. We have our wave function, but we don't know what the normalization constant is. So we just put n in there, capital N, for normalization. So do you see our wave function that we used earlier, that we did with the slinky? It wasn't normalized because the maximum was at 1, and we need the area under the curve to be 1. So we've got to reduce it a little bit with this factor n. So we have it twice, we have it squared. And so we're going to simplify these things. We're going to pull n out front, and we're going to have sine squared. And we're going to do the integral of sine squared. Well, you could probably look that up, but let's go ahead and figure out how we can reduce the power of that sine. I've got my integrals memorized. I have to do it derivatives and then reverse it. So what's the derivative of sine? It starts out with a slope of 1. And so cosine of 0 is 1. So the integral of, the derivative of sine is cosine. Okay? So cosine starts out, the slope at 0 is 0, and that's a sine thing, but it tapers down. And so it starts out with the slope of 0 and then goes negative. And so the derivative of cosine is negative sine. It's the opposite direction. And then the derivative of negative sine is negative cosine, and the derivative of negative cosine is positive sine. So it goes in that loop. It goes sine, cosine, negative cosine for your derivatives. Okay? Integrals are just the reverse. Okay? So we're taking the, but I don't know what my integral of a sine squared is. I've got sines and cosines. I can do those integrals because I've memorized that pattern. Sine, cosine, negative cosine for the derivatives. But I've got to figure out what to do with the sine squared. So we go to our trig substitutions. So we can reduce that power by doing this trig substitution. Sine squared is equal to 1 minus cosine 2u over 2. So I'm looking at that. So I've got to use that u substitution. So all of that piece in the middle is u. So I've got to double it. And then I've got to divide everything by 2. So I'm going to end up with two integrals. The 1/2 piece and the cosine over 2 piece. Okay? And so I'm going to take that, I'm going to substitute in, and this is what I get. I get all of these things here. You can see this 1/2, this integral 1/2 piece right here came from this one right here, this 1/2 piece right here. And then you can see my n pi over 2 has been changed. I had to multiply the inside by 2 here, and so I got rid of that n pi over 2. They canceled. But then I have this extra 2 right there. Okay, and then I have the 1/2 here in front because it was cos 2u over 2. And I've got a negative sign. Don't ever drop your negatives. That was always my problem in calculus. I would do a problem and it wouldn't work out. It was because somewhere in there I had dropped a negative. So attention to detail is important. So then I'm looking at this. I can make that into 2 integrals. Okay, so we have an integral. That's just one of the easiest integrals. It's integral of dx. When I take the integral of the derivative of x, I get x. So that one's going to be super easy. This other one is going to be the integral of cosine. So I take that, the integral of cosine is sine, and I've got to pull that stuff out front, the stuff that's in front of x. I pull it out front and invert it. Okay, I take the antiderivative, in other words. So the L comes out on top, the 2n pi comes out on bottom. Where does the 4 come from? Well, there was a 1/2 in front. So when the 2 came out on bottom, there was a 2 already there. They're multiplied by each other, and I get the 4. That's pretty straightforward. And you're like, yes, I did have to take calculus. Okay. So here we have our integral. Now it's wherever there's x, we're going to put in a L over 2, and then we're going to write everything again, and we're going to put in a minus L over 2. And then we're going to take the difference between those two. So we're going to take these 2 terms and we're going to turn them into 4 terms to take that difference. So here we have it, and I've color-coded it for you. So this first integral result is n squared over 2 times x, and it comes out and gives us these 2 terms right there. And then this next one, don't forget your negative signs. It's a negative here, and then I'm subtracting the lower part, so it becomes a positive on this side. And so this one produces these 2 terms. Now we can simplify a lot of things. Notice that a lot of the L's cancel. Okay. And so these L's cancel here. This 2 cancels there. We have an n pi and an n pi, so that's going to be 2 n pi. Here the L's cancel. The 2's cancel. And I have an n pi minus an n pi. And so that ends up being sine of 0. And so when we simplify all of these things, I have these first 2 terms where the L's didn't cancel. Let's see, where's my pen? Here we are. All right, so these 2 terms have simplified some, and they're right there. But these 2 terms, I ended up with a sine of 2 n pi and a sine of 0. Now think about sine. So at 0 and pi and 2 pi and 3 pi, what does sine look like? Let's see if I can draw this. It goes up and crosses 0 at pi. It goes down and crosses 0 at 2 pi. It goes up and crosses 0 at 3 pi. So every integer multiple of pi, the sine function is 0. So that's a great, easy integral result. I don't need to do anything with all of this. After I've simplified it algebraically, this piece is 0. And this piece is 0. So that's something that you need to know. And I even think I have a question like that on maybe on one of the homeworks or on the first exam of evaluate this result. And you're looking at it and you just need to recognize that integer multiples of pi in the sine function of integer multiples of pi is 0. Now, what if it was cosine? Well, integer multiples of pi for cosines alternate. The even ones are +1, the odd ones are -1. So they hop between plus and -1. So, but still a pretty simple result because we have integer multiples of pi. So once we get to the end and we have these two terms combined, we have a fourth plus a fourth, which is a half. Okay, and so we have n squared L over 2 is equal to 1, and we want to solve for n. So we bring the 2 over here, the L over there, and we take the square root. So n is equal to the square root of 2 over L. And that is the thing that we can put in front of our wave function as a normalization constant that will make the area under those curves equal to 1. So that was our goal. And it was very simple. We just did the integral over all space of that wave function squared. Okay. And those who just came in, the roster's kicking around. I think it's over there. Y'all can sign. And you can catch up on the video. All right. So now, see how wave functions no longer touch 1. They're smaller because they've been multiplied by the square root of L over 2. I mean 2 over L. And so that it adjusts with L, and it adjusts, all of it adjusts with L. So that's good. So now we have all of our criteria. Notice that the first 4 were just those criteria that really the first 3 were those criteria for any wave function. Then we also wanted it to be 0 at the boundary, centered on 0. It has to have quantum numbers, and it has to be normalized. So here's our wave functions inside the box. The walls of the box, the potential goes up to infinity abruptly, and so that's why they have to go to 0 at the edge of the box. They wouldn't have infinite potential. So they're inside here with the 0 potential inside the box. And then we haven't done the energies yet, we will, but that's the energy equation, and it's a function of the length of the box and the quantum number. And so this has been offset by the energy and actually multiplied by 200 on this scale so that you can actually see that the wave functions look bigger. But I just scaled them up 200 times just so that you could see them on the chart. If I didn't scale them, they'd be really close to that line. Yes?
When you're saying they don't have, or they would not have infinite potential, that's just because we're talking about it being in a box.
Yeah, it's captured in the box. Yeah, so there are some problems. Because I wanted this course to be more applied, I've shortened the quantum mechanics part. But in a lot of courses, they don't worry about applications and they just play around with the math for a lot. And so they'll have a box with a tiny little barrier in the middle, and they'll look at tunneling, and that's pretty cool. You have a wave function that starts out on one side of the box and it leaks through the barrier because the barrier doesn't go to infinity. And so then they can calculate the tunneling current and so on. And that's actually a good model for like a scanning tunneling microscope. So there's quantum effects in like scanning tunneling microscopy where the wave function of that electron, you get close enough and there's a non-zero probability that the electron will jump the gap just in a quantum mechanical fashion. So there's places where that barrier would not be infinity is my point. Yeah, but not in our course. Now let's think about the integral over all space. We're saying that integrating over all space, which is the whole box, the probability of the particle being found is 1. But what if it's just the first 10% of the box? Okay, so let's think about, I've got a box, and let's take a shoe box and put a dice in there, and I shake it up, and I rattle it randomly, and then I open it up, and I do this 10,000 times, so I get good statistics. I'm going to have an equal probability of that dice being in every part of the box. Okay, so like the first 10% of the box, the probability would be 0.1. If I did half the box, it'd be 0.5. If I did 25% of the box, it'd be 0.25, because it's a huge classical system. But if I square the wave function and look at the area under the curve, in the ground state, that is not 10% of the area under the curve. So let's look and see what that is. This is the probability of being in the leftmost 10% of the box. So it's just the area under this little curve right here. And it's that right there. So that's 0.1. This is let's see, 01, 02, 03, 04. Yeah, this is 0.01. So it's like less than a 1% chance that it'll be in the first 10% of the box. That's called a quantum effect. That's not a classical statistical sampling of a macroscopic particle in a box. Okay? And if you'll notice, sometimes it jumps up above what the classical probability would be. Here, It's like 0.13 or 125 of being found in the first 10% of the box. But look what happens as we go up in quantum number. The quantum effects die out, don't they? Smoothly. They start approaching the classical value of 10% chance of being in the first 10% distance of the box. But there's no abrupt change. It's just as the quantum states get lower and lower towards the ground state, the quantum effects become more and more pronounced. Okay? Now, one way to change this, to populate more energy levels, is to make the box bigger. So if we increase L, then it's easier to excite the molecules or atoms or electrons that we have in our box. Because L is in the denominator of the energy. So when you increase the size of the box, all these energy levels crush down, and you're going to have atoms, ions, molecules in the 100th or 200th or 1000th quantum state, where the quantum levels or the quantum effects just aren't detectable. Okay, you have so many maxima and minima and nodes that you can't even see that it's a wave. It just looks like a constant value across the whole box. So, now let's prove that the wave functions are orthogonal to each other. So when n and n prime are not equal to each other, the integral over all space produces a zero result. So we'll take our normalized wave function and we'll just do this and see what the result is. So we have this, we're going to take the integral of our wave function squared, but now n and n prime are not the same, so we can't make a sine squared out of it, right? You can only go from sine times sine to sine squared if the arguments are the same. But we have different arguments. We have an n prime in one of them and an n in the other. So this has to stay sine times sine. We can pull the constants out front. Okay, so we can pull that 2 over L. There's two of them, so when they multiply by each other, you get rid of the square root. So the 2 over L is out front, and we have sine of AX times sine of BX, if you want to think of it that way. And I know my integrals of sine and cosine, but I don't know the integrals of sine AX times sine BX. So maybe I could do another trig substitution. Anytime you have two sines of AX and BX, you end up with a cosine of AX plus BX plus a cosine of AX minus BX. And so this is what we end up with. Actually, it's the difference, not close. But you have n prime and n's subtracted and n primes and n's added. So that's a trig substitution. And now I've separated my trigonometric functions. And I have two separate integrals, and it's a simple integral of a cosine. Yes?
You divide by 2?
Mm-hmm. Yes, and there's a 1/2 in there too. So that's where the 2 disappeared up front. Great comment. So then I can look at this. I can do my integral with my cosine. Okay. What I just showed here is now I can do two integrals. So I distributed my integrals, and then the integral of cosine is sine. And I pull this piece in front of the x, I pull it up front upside down. Now, there's an L there, so when the L comes out, it cancels with the other L. So I have 1 over this piece times the sine, evaluated at L over 2 and minus L over 2, and then I have the minus sign. The L came out front, canceled with the L, and I have this piece upside down, and then I evaluated at L and L over 2, plus and minus L over 2. So once again, we end up with this piece times the sine, and it's an integer. So differences in integers are also integers, right? You can kind of look at that in your head and you say, yeah, any integer like a 3, even negatives too, like a 3 minus negative 2, okay, it's going to be 5, So they're all going to be integers. So this is integer multiples of pi here, integer multiple of pi here, here, and here. So all of those are 0. And so our orthogonality condition is satisfied. So if we take, when n and n prime are different, we multiply them together and integrate over all space, we end up with a result of 0. So our wave function is orthonormal. It's normalized and it's orthogonal. So it's a beautiful thing. And we can show it all on one page. Can't do this with the hydrogen atom. Because you have r, theta, and phi. and it's an enormous thing, okay? But you can do this with a particle in a box. So. Now let's talk about observables. That was all postulate 1. That was wave function, okay? And the probability distribution. Postulate 2 is that every measurable property that exists has a corresponding operator that goes with it. So what is an operator? Well, it's something that operates on the function. And so things like derivatives and integrals, those are operators. So here's the different observable in nature, if you will, and the different quantum mechanical operators. So momentum has this operator that introduces an imaginary, that I. Kinetic energy operator, the second derivative of the wave function. So that's something you need to incorporate in your mind, that the second derivative of the wave function is proportional to the kinetic energy. Okay, the second derivative of the wave function is proportional to the energy. We know the first derivative is called slope. What's the second derivative called? Conceptually, when you're talking about a curve. I'm not sure, because it's been a while since I have mechanics, physics, but there's another, just a mathematical term for it. It's curvature. So think about the curve. The more it curves, the higher the kinetic energy. We saw that with the slinky, didn't we? Right? The ground state kinetic energy was pretty low. But to get to that third or fourth excited state, I had to shake it like crazy. So the more it curves, the higher the kinetic energy. Second derivative is called the curvature. It's the slope of the slope. It's how the slope changes over space. So the curvature of the wave function is the kinetic energy, how fast it's going. And we see that. If it crosses the 0 point, it has more nodes, it's got more curvature, it has more energy. And then the total energy is the potential and the kinetic added together. So you have the kinetic piece here and the potential piece here. And this is the Hamiltonian operator, and that's what we're going to use to calculate the energy of our wave functions. Postulate 3. The measurement of an observable will yield an eigenvalue of the corresponding operator. So these are eigenvalue, eigenfunction equations. So the properties of the wave function and the operator will cause the system to be quantized, and the eigenvalues are the quantized observables. So let's look at that. Let's solve the Schrodinger equation to calculate our energy eigenvalues. And this is an eigenvalue equation. Eigen means same. It's German for same. So what do we see in this problem that's the same? Look at the left side and the right side. What's the same on both sides? The wave function. Yeah, very good. The wave function. It's the same. So we operate on the wave function. See over there on the left, that Hamiltonian operator has the second derivative in it. So we're taking the second derivative of the wave function, and it comes back. So we get that wave function back, and the constants of that second derivative come out front, and those constants are the energies. So we need functions that, when you do the second derivative, you get the function back. Well, let's think about sine. I take the derivative of sine, I get cosine. I take the derivative of sine, I get negative sine. But I get sine back, and a -1 out front. So that's the eigenvalue equation with just on sine by itself, with none of the other stuff in it. Let's do it with the stuff inside. So here's the kinetic energy piece. The potential energy is 0. That's convenient. So the kinetic energy piece multiplied by the wave function is equal to the energy times the wave function. And so we're just going to work on the left side of the equation, and then at the bottom we'll compare the constants out front to E, and they'll be equal to each other. So let's take the derivative. We've got to do it twice. It's the second derivative. So we'll do it one time. Okay, so taking the derivative of sine, we get cosine, and we get the pieces that are inside, they come out front. So we get an n pi over L out front. We've taken the first derivative. Now we take the derivative of cosine, and we get negative sine, so our negative sign goes away out front here. And we get another bit of the n pi over L. So this piece right here comes out front again, gives us the square. cosine going to minus sine, we lose this negative sign here. So this goes away. And going from cosine, second derivative of cosine. And we have our wave function back. So we started out with this whole thing of the normalization constant, square root of 2 over L times the sine of all of this business. And so we got that back. And so then this energy is equal to all of this stuff here. So we've solved for the energies of the quantized system, the particle in a box. We solved Schrodinger's equation. That's nice. Pretty easy in one dimension. Yeah. So here's our equation. Now remember, h bar is h over 2 pi. So okay, so we have a pi squared in the denominator and a pi squared up here. So that's going to kill that pi. And then we have a 2 squared in the denominator, which multiplied by 2 gives us 8. And so we see that 8 ml squared in the denominator, h squared in the numerator, and the quantum number squared. Now I've pulled it out because we kind of have this factor in front that has information about our system, the mass, the size of the system, and that's sort of a physical constant related to the system and then the quantum state of that system. So that's our energy equation for a particle in a box, and we will be referring to that all the time. Why? Because it's a great analogy. What happens when the mass of the system increases to the energies? This is going to give us all our energies. So what happens when the mass increases? Mass is in the denominator, so all those energies shrink down. And you stop being able to see the quantum effects. So when I go to an electron, the smallest easily measurable particle, the energies are really far apart because that's the smallest mass, 10 to the minus 31 kilograms. Okay? But I go to a proton, 10 to the minus 27. I go to a baseball, no quantum effects. Okay? What about the size? Well, if I want to get quantum effects of an electron, I need to put it on a really tiny wire. So I need to put it on like a 7 angstrom wire. I put an electron on an antenna on my vehicle, no quantum effects. Okay? So the size of the system, the quantum effects drop down. The mass of the system, quantum effects drop down. So that's why we don't see quantum effects just, like position is quantized. But wave function is so small. Okay? So you don't just see me hop from position 1 to position 2. My translational motion may be quantized, but we can't measure it. It's so small because my mass is so big. Okay. Now, postulate 4, expectation values. Well, the energy that we just calculated, it was an expectation value. Okay. This is another way to write that equation. So our expectation value of energy would have had a wave function in front. We brought it over here on this side. So we have the operator times the wave function and left multiplied by the wave function and integrated overall space. That's another way to write the Schrodinger equation. And then if it's not normalized, you can divide it by the normalization constant and it'll correct for non-normalized wave functions. So these are the expectation values of our energies written a different way. So that's the energy of quantum state 1, quantum state 2, quantum state 3, quantum state 4. So this is another way to write the Schrodinger equation. That's all. And then in terms of spectroscopy, we've got one last thing to cover that's important. The energy lines are differences in energy levels. So once we've solved for quantum state 2 and quantum state 1, the spectral line that will show up will be the difference of those two. So that delta E is the difference between those energy levels. And that's where we get our transition equations. So the difference in energies we could put in algebraically using this change in n, delta n. And I want you to do this for the homework. I think it's one of the assignments on the homework is to calculate the transition equation for a particular delta n, whether it be delta n of 1, so you're jumping 1 state, or 2 states, or 3 states. And here's the algebra for that. It's very simple. It's just like FOIL, right? And you multiply the squares n plus delta n squared. So do FOIL on that first, outside, inside last. And then simplify things, the n squareds cancel. And then you can simplify the fraction. And this is a common way to write it, where you have all these constants out front and the quantum number plus some small variable. That's for change in energy. Here's for the change in frequency. And you invert that to get the wavelength. And there's the speed of light involved too. So these are your three transition equations. And again, I wanted to get to that just because it's on the homework. The last one's time dependence, and we're not going to do anything with that. But it does take into account that imaginary piece that I was showing with the rotating wave function. All right.